Anything I can answer for you?
I need to upload more ODPs.
So I'm going to post an ODP over the weekend. It will be due on Tuesday, so you don't have to actually start it until Monday. But I've had some requests to put some ODPs up for stacks and queues, so I'm going to start that on. I'll make it available on the weekend, but you don't have to actually work on it on the weekend unless you want to. So it'll be, the first one will be Tuesday morning, and then I'll start a few after that, 24-hour thing. And those will be on stacks and queues. So, is everybody good on how to use Valgrind to check for memory leaks in PA2? I can go over it. So, Valgrind is pretty straightforward. I have no idea what this does. Hopefully it doesn't like wipe out my code though. So it does some stuff. So this is my program I'm about to turn in. I want to know if there's any memory leaks. So just say Valgrind and then the name of your program. Run your program normally. If it wants input, type in your input and so on and so forth. When your program exits, you get this report from Valgrind, and you want to pay attention to the heap summary. So this says in use at exit 4 bytes. That's a memory leak. Okay, if it says 0 bytes in 0 blocks, no leaks are possible, that's what you're looking for. If it says you've got something in use, then it'll give you a leak summary. So I definitely lost 4 bytes, so something is going on. The other thing is, I got all these messages in the beginning. This means you're doing something fundamentally that you shouldn't be doing. And it's possible that you might not actually end up with a memory leak, but if you're getting these kinds of messages from Valgrind, you're doing something funny in your code. And it may be that your program still looks like it's working correctly, but there's something you're doing that's not quite right. For example, you're freeing something that you didn't malloc, and it may be that what you're freeing isn't something that you needed anyway this particular time, but you might another time. Or you've got an area of a node that you wanted to point to null and you forgot to say set this thing arrow next equal null. And it turned out it was equal to 0 anyway because that's what your computer had in its memory at the time. And so your program behaved correctly, but you forgot to do an initialization. And another time it might be that won't have a 0 in it and your code will break. So these are like warnings, right? They're things that should not appear, and so they're worth taking a look at. But the main thing I'm going to check for is the leak summary, right? And make sure that there's no leaks. And we probably can't correct this because this is totally like random code. Let's just try this. I'm still going to get tons of warnings. But at the very end, my heap summary says in use at exit 0 bytes, 0 blocks. All heaps were freed, no leaks are possible. Okay, that's your goal. And for me, I got that to happen just by adding this one free J statement down here. All right, Pretty straightforward? All right, so just valve grind in your program. If you've got memory leaks, right, submit what you have anyway, because a memory leaks, I don't know, it's like 5 points or something. Submit what you have anyway if it works, right, and then spend some time trying to get rid of the leak. And if you can't, not a big deal, but see if you can get there. All right, any other questions on the GDB quiz yesterday? Do you want to run through the details of question 8 and 10? Raise your hand if you're interested in going through the quiz up here. Let's let me just start it then. So GDB temp G1, we start, and we've got this data 0, right, which is a my struct, and it's got the following fields. It's got X, C1, C2, Y, F1, F, and Z. They may actually be in that order since that's the way that it printed it out, but even if we don't know that, we can figure out where these things are stored as follows. If we print the address of data bracket 0, it's 601060. And let me do this on the board. So if you're watching at home, sorry. So 601060. So we can print the address of data bracket 0.x, and that's also 601060. And we can print size of data 0.x, and that's 4. So 60, 61, 62, 63, that's where x is stored. And so we can keep doing this. Print the address of data 0.c1, and that's stored at 64. And if we print the size of that, that's 1 byte. So this is C1. If we print the address of C2, that's 65. So we're making a memory map, right? If we print the size of C2, that's 1, so here's what C2 is. So we know what the first 6 bytes of our my struct looks like. 4 pieces of an integer, presumably, and then 1 byte for C1 and 1 byte for C2. All right, so let's print the address of Y, and that's 68. And if we print the size of Y, that's 4. So these 4 bytes correspond to Y. And you can do this for all of the fields. And when you do that, you'll discover there's 2 bytes here that we're not using. And somewhere else you'll discover 3 bytes that we're not using, and somewhere else you'll discover another few bytes, 4 bytes I think, that we're not using. And those 9 unused bytes make up the difference between the 23 bytes you calculated and the 32 bytes that are allocated. So the question that's asking you what's the first unused byte, right, it's going to be right there at the top of the red box. Any ideas why there's unused space in there?
Is that to make sure that everything lines up to a certain modulo?
Exactly, right? So this is what we call word alignment. And for technical reasons, if you're trying to do something with an integer and it starts at an address that's a multiple of 4, it runs a whole lot faster than if it doesn't start at an address that's a multiple of 4. And sometimes it's a multiple of 8 that we need. Sometimes it's a multiple of 32. But word alignment theoretically makes no difference, right? We could say our integer starts right here at 66, and it just takes up these 4 bytes. But the way architectures are set up in most computers, the memory is really not just a bunch of consecutive bytes. It's really organized by like 8 or 16 or 32 byte chunks. And when you fetch something out of memory, we usually fetch starting from one of these chunks, right? And if you go across a chunk, right, then you end up having to fetch from memory twice. And it'll totally kill your performance. So the compiler knows this, and it says, okay, I'm going to start y right here at a multiple of 4. And that's one of those things where architecture and hardware and software kind of come together. And we'll do a picture of the memory map. Hey, memory map. Okay. That'll make people pukey when they watch the video. All right. So let's go back to stacks and queues. And let's do some pseudocode. So let's start with a queue. And we're going to deal with a circular queue implementation. So remember, this is an array, and we have a head and a tail, and we can move both of them. And when we get to the end, we're going to wrap back around and start working from the beginning again. So let's run through an algorithm first, and then we'll do some pseudocode. But let's make a smaller queue. So let's just suppose our queue is a very tiny array, 5 elements. So we'll just call this queue, and we'll have a head, which is 0, and we'll have a tail, which is 0. So to insert, so which end do we insert at, head or tail? What?
Tail?
Tail. All right, insert at the tail. So q bracket t equals n, and then increment the tail.
So do you make the head and tail equal together?
They start off equal together, yeah. So let's insert prime numbers. So let's insert 3, 5, 7, and 11. So we'll insert a 3 here. Tail will become 1. We'll insert a 5. Tail becomes 2. We'll insert a 7. Tail becomes 3. We'll insert an 11. Tail becomes 4. So our tail is right here. Our head is still a 0. Head is telling us where to read from. So our remove code so r equals q bracket head, increment the head, return r. So if we remove 2 things, first time we remove head is equal to 0, we're going to return element 0, so that's going to return a 3, and head will become a 1. And then when we remove again, it's going to return element 1, because that's what head is, so it'll return a 5, and head will become 2. So now our queue looks like this. So one thing to note about this, the 3 and the 5 are still in the array. We can't like remove them from the array. We could replace them with something, but that would be kind of artificial. So the 3 and the 5, even though they've been removed from the queue, are still in memory. They're still in the array. But because the head is pointing down here at location 7, if we say remove again, we're going to remove the 7. Okay, so let's insert a 13. So insert says store your number at the position pointed to by the tail. The tail is 4, so we're going to put our 13 right here. And then increment the tail is going to become 5. Okay, and a 5 is a problem because if we leave the tail at 5, the next time we do an insert, we're going to try to put something outside of the array, and that's an error. So the idea of the circular part is when our tail gets to be 5, send it back to 0. So we could do actually t equals t modulo 5. Or you could do an if statement. If t is equal to 5, set t equal to 0. All right, so after we incremented from 4 to 5, we should reduce it modulo 5. Tail is 0. So now the tail is sitting over here. And that's perfectly fine. When we remove, we're going to remove the 7, and then the 11, and then the 13. When we insert, we're going to insert here, and then here, and here. So let's insert one more thing. Let's insert a 17. So insert says go to the position of the tail, that's 0. Put your number right there, there's our 17, increment the tail. So tail's equal to 1. And it's pointing right here. So if you look at this in the debugger or print statements or something, it can be confusing what's going on, right? Normally the tail is moving to the left, so the tail should be on the left of the head. And it kind of is, it's just sort of wrapped around. And we've got this 5 sitting in there that we removed, and it's sitting where the tail is, right? And it can look weird, okay? But just keep this in mind. The tail is where we're going to insert, the head is where we're going to remove. They both move to the left. When they get to all the way to the left, they wrap back around to the beginning. So if I do a remove right now, I'm going to pick up a 7. If I do another remove, I'll get an 11 and a 13 and so on. If I insert, my algorithm is going to want to insert right here. But after I do that insert, I'm going to increment my tail, and my tail is going to become 2, which is also what my head is. And if my head and tail are equal to each other, that's how we said we know that the queue is empty, right? But that apparently is also what we know if the queue is exactly full. If we insert into this last space that's not used yet, we increment the tail, head and tail are going to be equal. So head and tail could be equal in 2 cases, when the queue is empty or when the queue is full. And we'd like to have a way to know the difference between those. So one way is to set a flag. And if you insert, increment the tail, and they're equal, set the flag to be true, and that flag means the queue is now full. But an easier way is just say right now the queue is full. Don't let the queue and head don't let the tail and head be equal to each other from inserting. So we've got 5 spots in our array, but we're going to say we can only have 4 things in our queue. So what constitutes our queue elements right now? 7, 11, 13, and 17. And our algorithm will say, okay, the queue is full. It's not an error, but we can't insert anything else. So in our insert routine, we do a check and we say, if we add 1 to the tail, will the tail be equal to the head? If the answer is yes, we say the queue is full. So we can throw an extra check in here. So if t plus 1 modulo 5 is equal to the head, we'll say the queue is full, and we'll refuse to insert anything else. And then our empty condition becomes simply if tail equals head, Q is empty. So at this point the queue is full. We can't insert anything. We could remove. So we could remove once. That'll give us the 7. So remove returns a 7 and increments the head to 3. Remove again will give us element 3, which is 11, and increment the head, so the head is now 4. And remove again will give us a 13 and increment the head to 5. And again, we've got to roll back over. So after we do increment head, we can say head equals head %5. So now we'll change the head to 0. And now the head is sitting here, the tail is sitting there. And as soon as we did that first remove, we could have done an insert because this test would not have said the queue was full. So if we do one more remove, we read the element at location 0, that's the head, that's a 17. We increment head to 1. Head and tail are both equal to 1, and that means the queue is empty. Right? No matter what we do, we're not going to read that 5 because we removed that 5 way back here. It's not part of the queue. It's part of the array, but that's different. Right? The array is always this big. The queue could be, you know, some little piece of it. And in general, this might be your array. And your queue might go from here to here, or it might go from here to here, or it might go from here to here. Right, so it's not always just starting at the beginning and going over to the left. So it can wrap around. But code-wise, the code is pretty straightforward. Right? Insert, store at position T, increment T, roll it over modulo 5. Remove, pull it out from element H, increment H, roll it over modulo 5. And then we can actually write separate functions. Is full is just T plus 1 modulo 5 equals head. And is empty is just T equals H. And that's pretty much all you need to implement a queue. How do you initialize? What do you have to do to get this thing into some kind of initial state with an empty queue? Cool. Just set T and H equal to 0 and you're done. Or set them to 1 or set them to 7 or something, but as long as they're equal, your queue is empty.
Why you put tail plus 1 modulo 5?
Because tail plus 1 says, okay, right here you mean? Oh, so when you're inserting into your queue, so if your queue looks like this is the head This is the tail. This means that all of this stuff is part of your queue, right? Basically everything is in your queue except for this one last element, right? And we can tell that the queue is full because if we add 1 to this, it's going to be equal to the head. So the general check is if t plus 1 equals h, then the queue is full. But there's always a possibility that the tail is sitting all the way over here and the head is back here in the beginning. And in that case, if we take t and we add 1, we get 10 or something, right? But if we roll it over, or 5 in this case, if we roll it over modulo 5, we see that it's going to be equal to the head. So it's mimicking what we do in the insert routine, which is after we insert, increment the tail, reduce it modulo 5. So that's where that's from. So that's all you need to make a queue, basically. Using an array. And you don't have to do anything funny, and in PA3 I'm going to ask you not to do anything funny. For example, if you remove something and the queue is empty, you could set your tail and head back to 0, right? That does no harm, but there's no need for it either. As long as tail and head are equal to each other, you know the queue is empty. But sometimes I've seen people, when they realize the queue is empty, they set tail and head back to be 0 for some reason. It doesn't hurt, but it changes things. All right, so what about a stack? So we have an array. And remember with a stack, so this is element 0, 1, 2, and so on. We always insert or push on this end, and we also remove or pop from that same end. So queue, you go in on one end, come out the other. Stack, you go in and out on the same end. So the only thing we really need to know is how much stuff is actually in this stack. And when we implement this in software, we're going to do something tricky. If we were to actually always store something at location 0, right, if we push something into location 0, we have to do what that stack of dishes is doing in the buffet line, which is all the other dishes have to get pushed down one spot, so that we have space for a new dish on top. And when we take a dish from the top, all the dishes have to move up one spot. So that's effectively saying, let's store this at location 0, but let's take all of these and copy them down one, right? That's an expensive operation. So when we implement this in software, we actually push and pop from the left side, right, from the higher indices. And so we keep track of where we're going to push or pop the next thing in our stack. And so we have something called a stack pointer. And I'm just going to call it SP. And I'm going to initialize SP to 0. And I'm going to put a comment here. And there's 4 or 8 or 16 ways this comment can be written, or this set of comments can be written. So we're going to pick one of these for now. So SP equals 0. Here's my comment. SP is where the next push is stored. So my stack pointer is always going to tell me where is the next place I should store something when I push onto the stack. So let's push some prime numbers. Let's push a 2. SP is 0. I'm going to store my 2 right here. And then I'm going to increment the stack pointer, so that the next time I push, I don't overwrite that 2, but I put it in location 1. So push, and let me just call this stack. So push a number n says stack bracket stack pointer equals n, and then increment the stack pointer. So I push a 2, it goes right there. Stack pointer gets incremented to 1. If I push a 3, I'm going to store that at location 1. I'm going to increment my stack pointer. Push one more thing, which is a 5. Going to store that at location 2. I'm going to increment my stack pointer. So you got the idea of pushing, right? We're just going to keep putting things in here, incrementing the stack pointer to tell us where to push the next thing. Okay, so how do we pop? What's the first number we should pop off right now? The 5, right? So a stack is last in, first out. So the last thing we pushed in was a 5. That should be what we pop off first. So we want to pop a 5. That's at location 2. How do we get location 2? By using our stack pointer? Subtract 1. Right, so how does pop work? Subtract the stack pointer, and then return stack bracket SP. So if we say pop, it decrements the stack pointer, becomes a 2, and we return the thing at element 2. That gives us a 5. If we say pop again, decrement the stack pointer becomes 1, return element 1, that's a 3. Now if I say push 17, where's that going to get stored in the array? Which one? 1, right. So stack pointer is equal to 1. We're going to store our 17 right here. And then we're going to increment the stack pointer. So now if I said pop, stack pointer is 2. It's going to subtract 1, makes it 1. It's going to return element 1. That's 17. So the last thing you push on is always the first thing that you pop off. And again, we popped off the 5 a few instructions ago. It's still sitting in memory. Right? We didn't remove it. We're just choosing to ignore it because we moved the stack pointer, so it's pointing to a lower index than that. But this is still sitting in memory. So stack pointer is where the next push is stored. And so in some sense, SP minus 1 is where we pop from next.
Why don't you just make stack pointer -1 to be able to start with?
And then do what?
You don't have to subtract 1. So if it's -1, then it's empty.
Okay, hold that thought for 2 minutes and we'll go and do that. But let's finish this version. So how do we know when the stack is empty? What's the value of SP? 0, right? All right, and how do we initialize? Just set SP equal to 0, which gives us an empty stack. How do we know when it's full?
Size of
31.
You mean like size of as in C or like size of in English?
Sorry.
Yeah.
The size of the
Okay.
actual stack.
Yeah,
when,
yeah.
When I is equal to the size of the stack.
Yeah, so if the stack pointer gets to the point where we're going to go outside of our stack, right, then it's full. If this is not an array, if it's just memory, we don't really know how big that is. So the stack's full when we get an error, basically. Okay, so this is one approach, but let's look at an equally good approach. So let's do version 2. So initialize the stack pointer to -1, right? Okay, so what does our push routine look like? Because we can't store at element -1, so it'll just be the opposite. So first increment the stack pointer, and then stack SP equals N. All right, and what about popping? All right, we're going to take the element at SP, that's what we're going to return, and then we're going to decrement the stack pointer. So stack pointer would start at -1. If we push a 2, we'll put a 2 in there, stack pointer becomes 0. If we push a 3, we put our 3 in here, stack pointer becomes 1. If we want to do a pop, we want to return the element at location 1. Right, so stack bracket SP, and we want to decrement stack pointer to a 0. If we do pop again, it'll give us element 0, and we'll decrement stack pointer to -1. So empty is just stack pointer equals -1. And init is just SP equals -1. So pretty similar to what we were doing, right? Our push was this, now our push is that. Our pop was this, now our pop is that. And the terminology is post-increment, pre-increment, right? Increment SP before we use it. So we can write this in the language of C. A pre-increment basically says stack bracket plus plus SP equals N. And this becomes return stack bracket SP minus minus. Right, decrement, I did these backwards. Decrement and then use SP. Use SP and then increment. With this approach, we want to increment before we use the value. So it looks like that. And here we want to use the value. And then decrement. All right, so this is a post-increment for push, a pre-decrement for pop. This is a pre-increment for push and a post-decrement for pop. They're equally good. They're just different. This is actually what a PIC processor does, I think. But the interpretation of stack pointer is different. So up here in version 1, stack pointer is where the next push was going to be stored. Down here, stack pointer is where the next pop is read from. We got other things we could do. We could initialize the stack pointer to 10 over on the left side of the array. And as we push, we could move things to lower and lower indices. And as we pop, we could bring it back to that 10. So if we think of our memory as going from index 0 and increasing to the bottom, the way we've been doing this, we start by putting things up here at the top and moving down when we push and move up when we pop. We could simply start at the bottom of our memory and move up when we push and then move down when we pop. And we can do that in two different ways, post-increment or pre-increment. But in that case, we're incrementing when we pop and we're decrementing when we push. But all your code is going to look like some version of this, right? It's just, is it the pluses or the minus for push or pop, and are they come before or after, right? But it's got to be consistent. If I pre-increment and pre-decrement, it's not going to work. So I wouldn't try to memorize this. I would try to work through it yourself and choose a way to do it and see if you can come up with pseudocode for implementing a stack with that style. All right, and for the PA, I think I tell you which one to do, whether you do post or pre. I'll post the PA later today, and we'll talk about it tomorrow. So that's general pseudocode for an array-based implementation of a stack and a queue. So questions on that? I mentioned we could also implement these structures using lists. And list implementations are a pleasure after all of that. So we can build a list, and in some cases for people who were having trouble getting their add function to work, I said, well, make a simpler add function first that just adds to the beginning of the list. Forget about sorting things. When you want to add a number, just make a new node, have your sentinel point there, and point to the old first node. Well, if you do that, you're basically building a push function. And every time that you want to push something, we just add that something to the beginning of a list. And when you want to pop, it's a simplified delete function. Instead of deleting a particular number, delete the first node of the list. So basically, whatever the sentinel is pointing to, have it point to what that node was pointing to. And that removes this, and just return its value. So list implementation of a stack is almost trivial. You make a simplified add and a simplified delete that always do their thing to the first node after the sentinel. And every time you push, it just shoves something in here, and effectively everything else gets moved down. And the last thing that you pushed will be the first node after the sentinel. That's the thing that you're going to pop. And then a queue is a little bit more work. You can insert by putting them right in the beginning. And to delete, to remove from the queue, you need to go all the way to the end and just remove the last node. So you make a while loop and you go through until you get to a node that's pointing to null, and that's the value that you're removing from the queue, and you make the previous node point to null and free that thing up from memory. So I may have you do a list-based version of a stack and a queue for PA3. I gotta decide. And it may give you some ODPs to work with the array-based version. And then you'll have experience with both. But I'll figure something out and I'll post it later today. So tomorrow I want to talk about PA3, and then I want to talk about some applications of stacks and queues, and we'll look at some real-world situations in computer science where we can use stacks and queues to do different things. And then we're going to start talking about trees next week. So that'll be the real fun stuff at that point. And I don't mean that sarcastically. It's actually really fun stuff. All right, so I'll see you tomorrow.